Good morning, student. So, in lecture number 11, from the subject Electronics Devices and Circuits, chapter number 1, that is Junction Field Effect Transistor. So, myself, Assistant Professor Madhuri Mulik from Department of Electronics and Telecommunication, Sharad Institute of Technology, College of Engineering. So, in chapter number 1, we have seen the what is that the JFET, then types of the JFET, after that working principle of n-channel JFET. So like that we have seen the characteristics of the JFET. So today in this session we are going to see the high input impedance circuits for the JFET. So before that we have to summarize which whatever the points we have covered in this chapter number 1. So we have seen the field effect transistor, then we have seen the n-channel construction, then characteristics of that the JFET, then transfer characteristics of JFET, then VI characteristics of JFET, so output characteristics of the JFET, then normal operating range of FET. So this is nothing but the point from this session, that is small signal equivalent circuits of FET. So here the models the behavior of the device for small variations of the input about the operating point. So it is known as the small signal equivalent circuit of FET. So here already we have seen the configurations, that is common source, common gate and common drain. So these are nothing but the circuitry. So in the configuration, one terminal is common between the input and output of the other circuit. So for the common source, the source is common. For the gate, common gate configuration, so gate terminal is the common for the input and the output. And for the common drain, the drain terminal is common for the input and the output. So that the common drain working as a source follower. Okay. So a relationship of this circuitry, that the gain, input gain, so it is minus gm, that is transconductance of load resistance. So likewise for the Cg and Cd, then the minus sign indicating that between the input and output there is a 180-degree phase shift. Then load resistance, input impedance, then output impedance, then output gain of that the circuit, then current gain of the circuit, and the last is the power gain of that the circuit. So this already we have seen in a previous sessions. Then biasing of JFET also we have seen. Then CS amplifier and variations in IDS with VGS we have seen. Now we are going to see the FET mid-frequency response. So it is for common source amplifier. It's shown to the right side of this slide. Okay, so this is nothing but the common source configuration, or we can say common source amplifier. So the mid-frequency circuit is drawn as follows. The coupling capacitor, that is Ci, that is input capacitor, and Cout, okay, and the one bypass capacitor, that is CSS, which is short circuited, so it is represented as a CSS. So input, output, Input coupling capacitor, output coupling capacitor, and bypass capacitor are short circuits. Okay. So the DC supply voltage, that is superposition, this is VDD. So the replace the FET with the hybrid H model. So the resulting mid-frequency circuit is shown below. So this circuitry is replaced by the hybrid H model. So the mid-frequency and the common emitter amplifier. So common source, it is exactly same to the common emitter amplifier circuit. So analysis of common source mid-frequency circuit, that is given. So for this circuitry, the voltage input gain, that is V out divided by V in, that is nothing but just we have seen that minus Gm into RL. But RL is nothing but the parallel of RD, small rd, capital RD and RL. Then input impedance, that is Vi by IR, that is according to the Thevenin equivalent RTH, where RTH is nothing but the R1 parallel with the R2. Okay, so that is RTH. Then output impedance, that is V0 upon I0 seen through the RL. Okay, so from this side. So here RD is parallel with the capital RD. Then output, voltage gain is equal to, from the output circuitry, V0 divided by Vs. So is equal to, it is nothing but the input voltage gain divided by input impedance divided by Rs plus Zi. Then the AI, that is current gain, is given by I0 divided by IR. So is equal to AVI Zi RL. And the power gain is given by input side power divided by, output power divided by input power of that the circuit. So it is nothing but the product of AVI into AI. So here the capacitively coupled common source amplifier, which is shown in B, analysis of CS amplifier to determine its low frequency function. For simplicity, R0 is negligible. So here we have neglected that R0. So the sketch of the low frequency magnitude response of CS amplifier, for which the three pole frequencies are sufficiently separated for their effects to appear distinct. So here that is gain in a dB, and this is the frequency for the which is plotted in a log scale. So this is the means that the 3 dB. Then after that, so from this side, first decade it is increased 60 dB per decade, then 40 dB per decade, then 20 dB, and at last it is approximately the 3 dB. So which is given by 20 log of Km at the maximum amplitude, or that the voltage gain. So determining the high frequency response of CS amplifier, equivalent circuit is shown in a figure A. And the circuit B, which is nothing but the simplified at the input and the output. Okay, input and output side, we have simplified that the equivalent circuit. So here that the C shows that the equivalent circuit with the CGD, that is capacitor between the gate and drain, replaced at the input side with the equivalent capacitor C equivalent. Okay, so CGD is replaced with that the C equivalent. The frequency response plot, which is that of a low pass single time constant circuit. So it is shown that low pass single time constant circuit. So we have seen the JFET for the high frequency and frequency response. So what are the uses of JFET? It is the small signal amplifier. Then it is used as a voltage control resistor, or we can use this JFET as a switch. So these are the uses of JFET. So this is the shows that the specification sheet for the JFET. So 1, 2, 3. So here the semicircle and flat portion is here. So here 1 is nothing but the drain, 2 is nothing but the source, and 3 is nothing but the gate. So what is the number of 2n? 5, 4, 5, 7. So these are the electric characteristics, off characteristics, on characteristics, and the small signal characteristics. So this is the data sheet for that, the general purpose N channel depletion JFET. So here case construction. Okay, so that is TO18. So 1, 2, and 3. So you according to the notch side, 1, 2, and 3. 1 is the source, 2 is the gate, and 3rd is the drain. So up to this we have seen the N channel working. So the P channel JFET operates in a similar manner as the N channel JFET. Expect that the voltage polarity and the current direction. So voltage polarity is different from that the N channel, because N channel VGS is a negative, but the P channel VGS is the positive. And for the N channel, that the VDD is the positive with respect to negative source, but here the polarity is changed for the N channel JFET. So this is nothing but the characteristics that clearly shows that VGS is the positive. So let us see the important advantages of FET over conventional transistor. So we know that the BJT and FET, two types of the transistors. So one is the bipolar and another is the unipolar. So let us see the advantage one by one. So it is the unipolar device, that is operation depends on only one type of the charge carrier, either hole or either electron. So at the starting of the chapter we have seen that FET is nothing but the unipolar device, because either holes or the electrons, only one charge carriers are responsible to flow of that the current. Then it is voltage controlled device. Why it is known as the voltage controlled device? Because gate voltage controls the drain current. So input voltage controls the output current. So that's why it is known as the voltage controlled device. What about the BJT? BJT is the current control device, because IC, that output current means collector current, is controlled using that the input current, that is base. Okay, so FET is the voltage control device and BJT is the current control device. Then it has very high input impedance, so that is from 10 raised to 9 to the 10 raised to 12 ohm. Then source and drain are interchangeable in most low frequency and applications. Again, low voltage, low current operation is possible when low power consumption. Okay, so the advantage is it is low power consumption, because it will work on the low voltage, low current. Then it is less noisy as compared to the BJT. Then no minority carrier storage, so turn off is the faster. Okay, here no minority carrier storage, so the turn off is the faster. Then self-limiting device, so the JFET is self-limiting device. Then if you see the size, so it is very small in size, occupies very small space in a IC. So that is the another advantage of FET, that is it is very small in size, occupies the very small space in the IC. Then low voltage, low current operation is possible in MOSFETs. Also, zero temperature drift of output is possible. So, zero temperature drift of output is possible. So, these are nothing but the important advantages of the FET over the conventional transistor. Then, the last point from this chapter is FET used for high impedance circuit. So, here the single stage high input impedance amplifier is shown. So A, B, C and D. These shows the A shows the common source here, common source amplifier with input impedance of 5 ohms shunted by that the 30 picofarad. Okay, shunted by the 30 picofarad. So if you want an input impedance only a few mega ohms, so you can use an N-channel depletion FET in a common source arrangement, for which a typical circuit is given in a figure A. Okay, so input impedance of only few mega ohms, then you can use this uh, circuitry which is shown in the figure A. So the next, that is B, which shows that common drain amplifier with input impedance of the 5 mega ohms shunted by the 2 picofarad. So while the input resistance is still only how much it is, 5 mega ohm, the shunt capacitance has been redundant to about how much it is redundant, about up to the 2 picofarad. Okay, so at the expense of voltage gain, that is A naught is equal to Gm into Rs divided by 1 plus Gm Rs, which has been reduced up to the 0.7. So this is nothing but the input resistance controlling gate bias resistor can be increased up to the 10 or even 15 mega ohm. So the leakage currents then make the circuit resistivity to the temperature. Okay, so the second is the common drain amplifier. Then third, C, that is common drain temperature stable amplifier with 15 mega ohms 5 picofarad input impedance. Okay, so the common drain which is nothing but the source follower circuit. So gate bias resistor, okay, gate bias resistor bootstrapped gives uh, here bootstrapped gives high input impedance with better high temperature stability. Okay, so because the gate resistor network has the relatively low DC resistance, that's why these circuit C gives that the temperature stable amplification. Then next, D is nothing but the capacitor bootstrapped amplifier with input impedance of the 5 mega ohms with the 3 picofarad capacitor. So in figure D, that alternative arrangement of the sometimes used where 20 picofarad that the capacitor bootstrapped the 1 mega ohm 20 picofarad is bootstrapped with the 1 mega ohm gate resistor to give an overall input impedance of approximately that the 5 mega ohms shunted by 3 picofarad. So this is the capacitor bootstrapped amplifier, the input impedance of the 5 mega ohm to 3 picofarad. So when we using that FET for a high impedance circuitry, there are little bit the different circuit arrangement. So it will gives you the specific that the application. So at that time you can use the either A, B, C or the D, that the high impedance circuit. Okay, so thank you. Here all the points from the first chapter we have covered here. If you want that the summarize the topic, then we will again keep one session where all that the summary of the chapter number 1. So here we have seen the JFET, then working principle construction, VI characteristics, then the biasing circuits, then the common configuration circuit, then frequency responses, as well as that the how FET is used for the high impedance circuit. Thank you.